Hi everyone, in this not so short video, we will go over what data visualization is, some of its key concepts, and then we will finally end with a demonstration of a small data visualization project. So what exactly is data visualization? Data visualization is the representation of data and information through visual elements such as charts, graphs, maps, and diagrams. The goal of data visualization is to make complex data more accessible, understandable, and actionable by presenting it in a visual format that is easier to comprehend and analyze. By using different types of visualizations, data can be presented in ways that allow users to identify patterns, relationships, and trends that might not be apparent when looking at the raw data. Data visualization can also help in identifying anomalies, outliers, and patterns in large datasets, making it an important tool for data analysis. Data visualization can be used in various fields such as business, science, and education to communicate and present data in a way that is more meaningful and impactful. With the help of data visualization, user can make better decisions based on data-driven insights and perform tasks effectively. There are different ways to approach the requirement of data visualization, but one of the most commonly used framework is the data user task or the DUT model. According to this model, the three main requirements of data visualization are data, users, and tasks. The first requirement of data visualization is the availability and the quality of the data itself. The data must be relevant to the problem or question at hand, accurate, complete, and up to date. In addition, the data should be structured in a way that facilitates analysis and visualization. Data preparation and cleaning are critical steps in the data visualization process, as the quality of the visualization depends heavily on the quality of the data. The second requirement of data visualization is the user who will be interacting with the visualization. Users can be broadly classified into two categories, primary and secondary. Primary users are the ones who need to make decisions based on the data, while secondary users are those who support the primary users by providing context, interpretation, or feedback. Users can have different levels of expertise, backgrounds, preferences, and goals, which can affect the design and presentation of the visualization. Therefore, data visualization should be user-centered, meaning that it should be designed with the user's needs and expectations in mind. User research and testing are important methods to ensure that the visualization is effective and usable for its intended audience. The third requirement of data visualization is the tasks that users need to accomplish with the visualization. Tasks can vary depending on the user's roles, domains, and goals, but they can be broadly categorized into three types: exploratory, explanatory, and confirmatory. Exploratory tasks involve discovering patterns, trends, or anomalies in the data and require a high degree of interactivity and flexibility. Explanatory tasks involve communicating insights, hypotheses, or recommendations based on the data and require a clear and concise presentation of the findings. Confirmatory tasks involve testing hypotheses or validating assumptions and require rigorous and systematic analysis of the data. Data visualization should support all three types of tasks, either through a single visualization or through a set of linked visualizations. Task analysis and design are important steps in data visualization process as they help clarify the user's needs and expectations and guide the selection and customization of appropriate visualizations. In the data visualization space, idioms refer to a common design pattern or visual representation that are used to encode and convey data. Idioms are based on established conventions, norms, and best practices in data visualization, and they help the users to recognize and interpret the data more easily and accurately. Some common idioms in data visualization include bar chart. Bar charts are used to compare the values of different categories of variables using horizontal or vertical bars. Bar charts are useful for showing relative differences in size, quantity, or frequency. Line charts. Line charts are used to show trends or patterns in data over time or across different values. Line charts are used for identifying changes or variations in data over a continuous scale. Scatter plots. Scatter plots are used to show the relationship between two variables by plotting each observation as a point on a two-dimensional graph. Scatter plots are useful for detecting correlations or clusters in the data. Heat maps. Heat maps are used to show the distribution of values in a matrix or table using colored coded cells. Heat maps are useful for identifying patterns or clusters in a large dataset. Tree maps. Tree maps are used to show hierarchical data using nested rectangles or squares that represent different levels of categories. Tree maps are useful for visualizing the relative size or importance of different subgroups within a large category. By using these and other idioms in data visualization, designers and analysts can create effective and efficient visualizations that help users to understand and interpret the data more quickly and accurately. There are a few limitations that come up when we talk about data visualizations. They are mainly categorized into three fields. That is the limitation of computation, the limitation of human perception, and the limitation of display. In terms of computation, the size and the complexity of the data can sometimes exceed the capacity of computing systems, making it difficult or impossible to create visualizations. For example, large data sets with billions of data points may require specialized hardware or software to create meaningful visualizations. In terms of human perception, our visual perception can also limit the effectiveness of data visualization. For example, our ability to distinguish between different colors, shapes, or patterns can be limited by factors such as color blindness, visual acuity, or cognitive load. Memory and retention also play an important role in the limitation of human capabilities. Sometimes it is not easy for us to memorize categories and then compare them. In terms of the display or the presentation of data visualizations can also pose limitations. For example, the resolution and the size of the screens or print media can affect the level of detail that can be conveyed in a visualization. Additionally, the format of the display can impact the interpretation of the data, with some formats being more effective for certain data types than others. To come up with a good visualization, we look for insights. Insights in data visualization are key pieces of information or knowledge that can be derived from the data through the use of visual representations. Insights help to uncover patterns, trends, relationships, or anomalies in the data that might not be immediately apparent through other methods. The key features of a good insight are that it should be of deep understanding, meaningful, non-obvious, actionable, and based on data. I will try to explain them in more simpler words. Uh, a good insight should have the following key features. It should be relevant. A good insight should be relevant to the problem or question being addressed. It should provide valuable information or knowledge that can help make informed decisions or help in making advanced understanding. A good insight should be clear and easy to understand. It should be presented in a way that is accessible and understandable to the intended audience. A good insight should be new or surprising in some way. It should challenge the existing assumptions or reveal new perspectives on the data. That is, a good insight should be novel or non obvious. Actionability. A good insight should be actionable, meaning that it should provide a basis for making decisions or taking actions. It should be a clear direction or next step based on the information presented. Robustness. A good insight should be robust, meaning that it should hold up and under different conditions or assumptions. It should be supported by evidence and not be overly influenced by outliers or other anomalies in the data. Overall, a good insight should provide clear and valuable understanding of the data, and it should be presented in a way that is accessible and actionable for the intended audience. Here we have a graph of the tools which represents the tools that are more commonly used for data visualization. We can see here that the ease of use of a tool is inversely proportional to its expressiveness. We do have a sweet spot though, which is the visualization grammar. We can use tools such as ProtoViz and D3.js to have the best of both category, the ease of use and making the visualization as expressive as possible. Let's talk about what problem abstraction is when we try to tackle a data visualization project. Problem abstraction in data visualization refers to the process of simplifying or distilling complex data into a form that is more easily understood and analyzed. The goal of problem abstraction is to identify the key features or patterns in the data that are relevant to the problem or question being addressed, and to present them in a clear and concise way. Problem abstraction involves several steps. The first step in problem abstraction is to identify the problem or the question that needs to be answered. This could be a specific research question or a broader business problem. Second, the next step is to collect the data that is relevant to the problem. This may involve gathering data from various sources, cleaning and transforming the data, and preparing it for analysis. Once the data has been collected and prepared, the next step is to explore the data to identify patterns, trends, or relationships that might be relevant. The final step is to abstract the data by selecting and presenting the key features or patterns that are most relevant to the problem. This may involve creating visualizations, summaries, or other presentations of the data that make it easier to analyze and interpret. There are 3 steps in problem abstraction: the what, why, and how. When we talk about what, we basically talk about what is being visualized. We talk about the data abstraction in terms of what abstraction. When we talk about why, we talk about why is the user looking at it. We basically do a task abstraction in this step. How is related to how a visualization is visualized. Basically, what are the marks and channels used to create an idiom? Let's look into them in further detail. Data abstraction is a critical technique for data visualization as it simplifies complex data, and it can also help identify the type of data sets and the attributes required to create effective visualizations. By abstracting the data, analysts can gain insights into the key patterns and trends in the data, which can in turn help make better decisions about selecting the appropriate idiom for the purpose of visualization. This can help improve the overall effectiveness and impact of the data visualization, allowing for a better communication of insights to stakeholders. We will look further into the types of data sets that are available and the types of attributes, or how we can categorize the attributes of a data set. Let's first talk about the types of data sets that are available. To start with, there are two kinds of data sets that are available, static and dynamic. When we talk about static data types, these are the ones that are not updated regularly. In fact, once they are created, they are left alone, and they will always remain the same. Whereas the dynamic data sets are the ones that are regularly or periodically updated. It can be The period of updation can be with every day or within weeks or months or anything. Uh, okay, there are the data sets are categorized into the following types: tables, multidimensional tables, fields, temporal data, tree data, networks, and spatial data. Tables are the simplest and most common form of data sets. They consist of rows and columns. They have one key and multiple values related to each key, whereas multidimensional data can have multiple keys. Spatial data is the data that is associated with a geographical location, such as population density or climate data. The data is often represented using maps or other geographical visualizations. Network data is the data that is composed of nodes and edges, such as social networks or transportation networks. This data is often represented using nodes, node link diagrams, and other types of network visualizations. The key difference between network and tree data is that in tree data, the leaf nodes are not really connected, or the nodes are not really connected to each other. In fact, they all sprout out from a root node. Whereas in network data, the nodes can be linked or not linked. Temporal data is the data that is recorded at regular intervals over time, such as daily stock prices or monthly sales figure. This data is often represented using line charts or stacked area charts. The attributes of a dataset are widely categorized into two types, that is, the categorical and the ordered. Categorical attributes are variables or data fields that contain data that is divided into distinct groups or categories. These groups can be mutually exclusive or overlapping. Examples of categorical attributes include gender, that is male or female, marital status, single, married, divorce, and job titles, manager, director, CEO, CFO, etc. Ordinal categories are categories that have a natural ordering or ranking, such as high to low, low to medium, or something like that. Ordered Ordered data is further classified into two types: ordinal and quantitative. Ordinal data is basically nominal data, but with an order. For example, the level of satisfaction. They can also be numbers, but we really can't do any arithmetic operations on ordinal data. Quantitative data, on the other hand, is composed of numerical values such as integers or decimals. The key feature about quantitative data is that we can use them for measurements or do mathematical operations on them, like the average GPA or the total marks, etc. Ordered data further has ordering direction associated with them. These are mainly categorized into three types. Sequential. In sequential ordering, the categories are arranged in a logical or natural order, such as low to high or small to large. For example, the ordinal data for education levels could be arranged in a sequential order as followed: elementary school, middle school, high school, college, and graduate school, and then doctorate. The second type is diverging. In divergent ordering, the categories are arranged around a central point or midpoint, with categories on either side that are increasingly dissimilar. For example, ordinal data for latitudes and longitudes could be arranged in diverging order, with the latitude and longitude of equator being the midpoint. The third type is cyclic, the third ordering direction, that is. In cyclic ordering, the categories are arranged in a circular or repeating pattern. For example, ordinal data for days of the week could be arranged in a cyclic order as follows: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday, with the pattern repeating every 7 days. Let's now look into the task abstraction, that is the second part of the problem abstraction. Task abstraction in data visualization refers to the process of identifying and simplifying the key tasks or goals that the user want to accomplish through the data visualization. This involves breaking down complex data into smaller or more meaningful pieces and identifying the specific questions that the users are trying to answer or the insights that they're trying to gain. Task abstraction can be simplified as actions that can be performed on targets. Good tasks are generally specific, measurable, numbered. They describe specific attributes and independent of the visualization. Actions and targets are important components of designing effective visualization that enable users to perform specific tasks. Actions are user tasks or goals that are intended to be achieved through the visualization. They can be simple tasks such as identifying a trend or pattern in the data, or more complex tasks such as comparing multiple datasets or making predictions based on data. Actions are usually expressed in terms of verbs such as compare, filter, explore, or explore. Target, on the other hand, are specific aspects of the data or the visual encoding that the user will interact with to achieve the desired action. Targets can include individual data points, attributes, or visual elements such as access labels or legends. Targets are usually expressed in terms of nouns such as data points, attributes, or visual elements. By identifying the actions and targets of a data visualization task, designers can create visualizations that are optimized for the user's needs and are more likely to be effective in achieving their intended goals. This approach helps to ensure that the visualization is designed with a clear purpose in mind and that the visual encodings and transformations are chosen to support the task. Let's look at some of the actions and targets on the screen here. We can categorize actions into three broad categories, that is analyze, search, and query. When we talk about analyzing a visualization, we rarely talk about consuming or producing a visualization. In consuming, we try to discover trends or features, or we try to present the outliers, or in general, just enjoy the whole visualization. In terms of produce, we either annotate or record or derive a distribution or extremes, or maybe the correlation or the similarity between the features. I will go over search at the end because this might be a little complex to understand. Let's go over query first. When we talk about query, we actually try to identify or compare or summarize the distributions or trends, or we actually try to identify the similarity between the different data points. We can try to compare the correlation or the distribution and the extremes. We summarize the we try to also summarize the whole of the distribution. Let's talk about search. So think of search as a data table where if the location is known, we can assume that the indexes in the data table are sorted, and we will what that means is, suppose we say we are looking for location 10, and in a sorted index we for sure know that 10 comes after 9 and before 11. So in terms of location known, we can think about it as a sorted index table. Whereas in case of location unknown, we can think of it as about an unordered an unordered indexed data set. So for example, in a data set which is not ordered by index, and the indexes are placed randomly, we will not really know where index 10 is unless we actually explore the whole of the data set. In terms of target, let's say we are trying to find out what is the value of an attribute that is at the 10th location. If we know the target, it is very easy for us to get to the actual value, because it will just be a cross section of the row and the value and the column. Row and the column. But if the target is unknown, suppose we know the value that we are looking for and we know the location that we are looking for, but we do not really know the target, or we do not really know the name of the attribute that we are going to look for, we will actually have to browse the whole row to look for that specific value in that specific location to get to the target. If the location is unknown and the target is known, we will now again have to locate the row number that will be based on a specific attribute. Suppose let's say we know the attribute name, that is the target is known, and we also know the value that we are looking for, but we really don't know what location or at what index that value might be. So we will actually have to go over the whole column to locate the location. When we do not know the location or the target, but we just know the value that we are looking for in the table, we will actually have to browse or explore. We will actually have to explore the whole of the table to get to that specific value, and then we can actually get to the target and the location of that particular value. Targets or the nouns are divided into four categories, four broad categories. That is all of the data wherein we talk about the trends, the outliers, and the features. Attributes can be one or many. When we talk about one attribute, we generally talk about its extremes or its distribution along a certain axis. In terms of many, we talk about the dependency of one attribute to another, or the correlation between different attributes given a certain common criteria, or the similarity between the different attributes. In terms of network data, we generally talk about the topology or the path of the data points. In case of spatial data, we talk about the shape of the data points that they take up when arranged in a particular manner or with a certain criteria in mind. The how abstraction, that is the third part of problem abstraction while doing data visualization. How abstraction refers to how the data can be presented using the idioms. While doing how abstraction, we take into account the marks and channels that can be used to effectively express the different types of attributes. To achieve maximum expressiveness, we need to match a channel and the data characteristics. We should use a channel that expresses that express that can express all of and the only information in the dataset. To achieve maximum effectiveness, we should encode the most important attribute with the highest rank channel. The channel's rank comes from its accuracy, discriminability, separability, and its ability to pop out from different attributes. Let's look further into what exactly are marks and channels, and how are they encoded in terms of data visualization. Some of the common marks used for data visualization are lines, points, and area. Bar graphs are also considered as lines because if they did not have the width, they would actually just be a line. There are various channels that are used to encode these marks. These are position, which can be horizontal, vertical, or both. Shapes, for example, different categories can be given to different shapes. Let's say we are talking about the types of business, and agriculture can be square, or um, education can be a circle, IT related companies can be a triangle, something like that. Size can be increasing length or growing area. Color combination, that is, colors are basically combination of RGB. There are two types of um, two ways in which we can use colors when it comes to using colors. It's hue and its luminance, or its saturation. The tilt of a particular mark can be used as a channel. For example, a line can be flat, it can be vertical, or with a slope of 45 degree. Marks can also have a channel. Marks can also have volume as a channel. That is, for example, in case of points or in case of area, we can have increasing or decreasing volume. And let's talk about encoding these different channels. So quantitative attributes are generally encoded in terms of express, that is a single express. We can think of it as an expressed quantity in bar graphs. The bars are, if we are using them to express a quantitative attribute, its length actually determines the length of the bar determines the value of the attribute. That is, the longer a line, the more the value, which is kind of express. Categorical attributes can be encoded in three different ways. That is, separate, order, and align. When we talk about separate, we generally mean that the data points are spread out on the visualization chart or amongst the axes with they do have a particular position, but they are not really aligned or ordered. In terms of order, we talk about the ordering of the values in a graph. Let's say for example, the order can be high to low or low to high. Over here in the diagram that is presented, it is basically an ordered data from low to high, though it is not really aligned. It can be aligned or unaligned. To explain that further, I would say a line is basically when we are trying to compare or measure values against a similar axis for all the attributes. Not similar, I would rather the same axis. the axis against which the different values are being compared is common for all the attributes. If this axis is not common, it is generally non-aligned. Aligned attributes can also be ordered, but they cannot be separate. I mean, yeah, the separate data points cannot really be ordered. Let's talk about how these channels are effective in terms of displaying certain types of attributes. For example, ordered attributes generally or are commonly expressed using these particular channels. We can use the position on a common scale, or that is an aligned scale or an unaligned scale. We can use the length of the lines or the bars in terms of ordered attributes. We can use the tilt of a line to express its value. For example, a low value is flat, whereas the highest value is 90 degree. We can also use the area. And like I said, there are different ways colors can be used. For ordered attributes, we generally use color luminance or color saturation, that is light to dark. What that means is, generally, it is perceived as the darker the color, the higher the value, and the lighter the color, the lighter the value. Let's look at the difference in the categorical attribute color channel. In terms of categorical attributes, the color luminance or the saturation is not generally used, because one color generally identifies one attribute. So in terms of categorical attributes, when they actually belong to when the attribute actually are not related and belong to different categories, it is advisable to use different colors for expressing different attributes. Other channels are that is spatial region, that is where a category is located. Its motion can be right to left, counterclockwise or clockwise, or we can also use different shapes to represent a categorical attribute. As you can see, I have a bar representing what are the most effective channels when we talk about ordered or categorical attributes, and the ones that are least effective. For example, curvatures. When we have multiple data points on a single graph, noticing this curvature will become a little hard, as you can clearly suspect. Even for example, let's talk about a scatter plot graph. Scatter plot graphs generally are not preferred because of the possibility of occlusion of data points. Let's say there is a big or let's say there's a big data point, because the value of that data point is large. And let's assume that there are a lot of data points with smaller values on a same location. The larger data point will possibly be hidden by the smaller data points, which will make the volume or the size of the point actually less effective in case of scatter plots, because again of occlusion that the scatter plots provide or generate. There are a few rules of thumbs when we practice data visualization. First of all, 3D is not really justified. That is mainly because the depth cannot be perceived correctly on a 2D plane. Most of our devices that we use for data visualization are 2D in nature. They're not really 3D, and it leads to loss of information. 2D planes do provide information with more ease, so they should be preferred over 3D planes. As 2D planes generally just require quick eye movements to read the idiom. Occlusion, like I was talking about in the previous slide in case of scatter plots, occlusion hides a lot of information. Interactions or collision prevention can solve the occlusion problem, but it comes at a cost of accuracy, since we will be moving the points so that since the points will not collide anymore, their original location might be lost. So the accuracy of the point will be lost. Tilted text is a poor choice of representation because of its poor legibility. Legibility basically refers to the ease of readability of a text. Maps should be used just for geographical data and not for comparisons. Having location in a data doesn't really mean that the task is geographical. Eyes beat memory. It is better to display as much information with marks and channels rather than text or animations, as that requires the user to memorize and correlate the information. Animations are a big no for comparison, as it again requires memorizing your last animation to the next one. Resolution beats immersion. That is, it is more important for the visualization to be clear than immersive. The visualization mantra is as follows. Overview first, zoom and filter, and then details on demand. To create a good visualization, focus on first providing as much information as possible on a single overview. And then to add more details, add zoom and filter, and at last focus on providing details on demand. As important aesthetics are, functionality does come first. Aesthetics can be improved later, but adding functionality later becomes tough. Making the idiom responsive helps, but it does have its negatives, because if you're trying to redraw the idiom every time there's an interaction, that can really be counterproductive. Access should always be labeled. We should avoid using dual access because that can make the reading of visualization pretty confusing. Some basic design principles are proximity, alignment, repetition, and contrast. When we talk about proximity, we really talk about grouping related items together, since it becomes easier for the user to identify the attributes. Alignment. When we talk about alignment, we talk about we talk about basically saving the white space, but altogether also using the space judicially. We should avoid default centering of text, for example. Um, Basically, the space that is provided for the visualization should be used effectively and not just scattered all over. Repetition. Um, we can achieve consistency by unifying similarities. Uh, yeah. Contrast. In terms of contrast, information can be made more noticeable by using contrast to pop it out. These are a few basic design principles that can be followed. Let's talk about representing tabular data. Tabular data can be presented in multiple ways. Some of the common ways are scatterplot, which uses zero keys but has values. One When we have one key in the table and we have multiple values, one key and multiple values, we generally tend to use linear or radial scale graphs. In linear scale graphs, we talk about bar graphs, stacked bar graphs, group bar graphs. In radial scale, we talk about radial bar graphs, star plots, radar plots, pie charts, and polar area charts. When we have two keys in the data and multiple values, we generally try to represent them using a heat map. When we have multiple keys and multiple values, we would rather use a scatter plot matrix or parallel coordinate chart. Uh, let's talk about some of the pros and cons of these different charts. In terms of scatter plots, pros are they can show relationship between two continuous variables. They can easily identify outliers and clusters in the data. They can allow for the identification of patterns and trends in the data. They can be used to identify correlation between variables and are generally easy to understand and interpret. Cons, they can be difficult to read when there are a large number of data points, and they if there are a large number of data points, they generally do not show causation and only correlation. They can be influenced by the outliers, which may skew the interpretation of the data, and they may not work well for data with categorical values. Also, scatterplot, like we talked about, can have occlusion if there are a lot of data points. Linear graphs, such as bar graphs, are generally easy to read, are useful for comparing data between different categories, can display both positive and negative values, can be used with both discrete and continuous data. Some of the cons of bar graphs are they may not be suitable for showing trends or patterns in the data, are limited to showing only one variable at a time, can be difficult to compare values when there are many categories. For stacked bar graphs, some pros are that they are useful for showing how different categories contribute to a whole, can be used to compare values between categories. Some of the cons are that they can be difficult to compare between they can be difficult it can be difficult to compare values between categories when there are many stacked bars. They may not be suitable for showing trends or patterns in the data like any other bar graph. Group bar graph again can be used to compare values between multiple variables. They are useful for showing trends or patterns in the data. They may not be suitable for showing how different categories contribute to a whole, and they can be pretty difficult to read and interpret when there are many bars. In terms of radial scale graphs, the radial bar chart is useful for showing how different categories contribute to a whole. They can be used to compare values between categories, but it can be difficult to read and interpret when there are many bars again. They may not be suitable for showing trends again because generally trends are shown using line charts. Star plot can display multiple variables at once. They are useful for comparing values between categories. They allow for identification of patterns and trends in the data. Some cons are they can be difficult to read and interpret when there are many variables, and they may not be suitable for showing different categories to show how different categories contribute to a whole. Radar plot. Some pros for radar plot are that they're useful for comparing values between categories. They can display both positive and negative values, and they allow for identification of patterns and trends in the data. But again, they can be difficult to read and interpret if there are many values, and they may not be suitable for showing how different categories contribute to a whole. A pie chart is easy to read and interpret, is useful for showing how different categories contribute to a whole, and they can be used for discrete data, whereas they can only display one variable at a time, can be difficult to compare, and they can be pretty difficult to compare values between different categories. Um, Generally, it's easier for humans to compare the heights rather than the arc or the angle of a circle or angle of an arc in a circle. Polar area charts are useful for showing how different but they can be a little difficult to read and interpret when there are many categories again. They may not be suitable for showing trends or patterns in the data. Heat maps. Heat maps can display a large amount of data in small space. They are useful for identifying patterns and trends in a data. They can be again used for both discrete and continuous data. Some of the cons are that they can be difficult to read and interpret when there are many data points, as again they will require some part of the memory to be in work, wherein you will have to compare what color represents what data point and what value. They may not be suitable for showing how different categories contribute to a whole. Scatterplot matrix allow for identification of patterns and trends in multiple values. They can display multiple variables at once and are useful for identifying correlation between variables. Uh, though a scatterplot matrix can be difficult to read and interpret, if there are multiple variables, we will again have to memorize a lot of data. And they may not be suitable for showing how different categories contribute to a whole. Parallel coordinate graphs. They allow for the display of multiple variables in a single graph, which can be useful for identifying patterns and trends in the data. They also allow for comparison of variables, which can be useful for identifying correlations between variables. They can display both continuous and categorical variables, and they can be used to identify outliers and clusters in the data. They can also be used to identify relationship between variables. There are multiple cons when it comes to parallel coordinates. They can be again difficult to read and interpret when there are multiple variables. They require some level of data preparation and pre-processing before use. They can be influenced by outliers, which may skew the interpretation of the data. They can be difficult to compare values between different variables and may not be suitable for showing how different categories contribute to a whole. They also require some level of familiarity with the graph to interpret the data correctly. Let's now talk about how we can represent temporal data. Again, temporal data is the data that is collected over a period of time or at regular intervals. Basically, it has an attribute that represents the time or the date or the year in which a particular value was collected. Different ways to represent temporal data are line charts, bar graphs, area charts, stream graph, Gantt chart, radial timeline, horizon chart, or joy plots. Let's look into them with more detail. Oh, a quick note. The granularity of data can be of two types. We can either truncate the date, that is year, month, date, year, month, day, hour, or we can actually use separate parts of the data to represent a visualization, that is just the year or just the month or just the hour. Though time is in itself a sequential quantity, that is a unidirectional attribute, it is ever increasing in nature, but there are parts of data that are cyclic in nature, like the month or the day of the week. Let us now look into the different types of charts. A line chart is a type of graph that displays data points connected by straight lines. It is useful for displaying trends over time or comparing data values between different groups. Some of the pros and cons are that it is easy to read and understand. It is useful for showing trends over time, can display multiple variables at once, and can be used with both continuous and categorical data. Though a line chart may not be suitable for showing how different categories contribute to a whole, and they can be influenced by outliers, which may skew the interpretation of the data. Bar graph. A bar graph is a type of graph that displays data using rectangular bars. It is useful for comparing data between different categories. They are generally easy to read and interpret and useful for comparing data between different categories. They can display both positive and negative values. and they can be used for both discrete and continuous data. Bar graphs may generally not be suitable for showing trends or patterns in the data and are limited to showing only one variable at a time. They can also be difficult to compare values when there are multiple categories. Area charts. An area chart is a type of graph that displays data using colored areas under a line. It is useful for showing changes in the data over time. It is especially used when we want to see the overall total, and also we also care about the actual value of each attribute. Area charts are useful for showing changes in the data over time and can be used for both continuous and categorical data. They can display multiple variables at once. Though area charts might not be suitable for showing how different categories contribute to a whole, and they can also be influenced by the outliers. Stream graph. A stream graph is a type of graph that displays data using stacked or flowing bands of colors. It is useful for showing changes in data over time. It is especially used when we want to see the overall total, but we don't really care about the actual value for each attribute. But we also at the same time want to see the distribution of each attribute. Some of the pros of a stream graph are that it is useful for showing changes in the data over time, can display multiple variables at once, and can be used for both continuous and categorical data. Though stream graphs might not be suitable in all the cases, they can again be influenced by the outliers, which may skew the interpretation. And they can also be difficult to read and interpret when there are many categories. Since they do not really have a center point or a point that aligns the streams, it also becomes a little confusing to actually gauge the particular value. Gantt chart is a type of graph that displays project schedules and timelines. It is useful for showing the progress of a project over time. They are useful for displaying project schedules and can display multiple projects at once. They can be used for both discrete and continuous data. Though a Gantt chart may not be suitable for showing how different categories contribute to a whole and might be limited to showing only time-based data. Radial timeline graphs or radial timeline is a type of graph that displays time-based data in a circular format. It is useful. It can be used for displaying timelines and events. They can show. They can again show both discrete and continuous data, and can represent multiple and can display multiple variables at once. But again, they can be pretty hard or difficult to read and interpret when there are multiple points. A horizon chart is a type of graph that displays data using overlapping colored areas. It is useful for showing changes in data over time. Again, they can be used for both continuous and categorical data and can display multiple variables at once. But they can also be pretty difficult to read and interpret when there are multiple data points. They also may not be suitable for showing how different categories contribute to a whole. Joy plots are type of graphs that display multiple data sets on a single graph. They are useful for showing the distribution of data. They can display multiple data sets at once, and they can again be used for both continuous and categorical data. Some of the cons when it comes to joy plots are that they can be difficult to read and interpret when there are multiple data sets or when the data sets have large number of values. They can be visually cluttered and difficult to distinguish between different data sets. They may not be suitable for comparing data sets that have significantly different scales of distribution. They can also be sensitive to the choice of bandwidth parameter, which can affect the shape and the density of the curves. Uh, Joy plots also may not be suitable for showing the exact numerical value as they focus on the distribution and the shape of the data. Um, with this, let us quickly go over one short example, and let's talk about how we tackle the problem abstraction to come up with the final visualization. Let's select this one. This is a reactive JavaScript notebook called Observable. I have used this to analyze the brain stroke prediction data that I got from Kaggle. Brain strokes are most common cause of adult disability in US and more or less everywhere in the world. Every year, more than 795,000 people in the United States have a stroke, with about 160,000 dying from stroke-related causes. Some of the common causes of stroke include stress, diabetes, high blood pressure, and smoking. Let us take a quick look at the raw data and then talk about few example insights that I will be analyzing or analyzing with my visualization. This was the raw data that is available on Kaggle. It includes various key value pairs like gender, age, hypertension, heart disease, their marital status, work type, residential type, the glucose level, BMI, smoking status, and if they've had a stroke or not. Um, to come up with a visualization, I chose the following data attributes. Here I have the data abstraction written in detail. Well, the dataset type is tabular and its availability is static, that is, it is not periodically updated, it is a constant data. The attributes that I've used are age, which is an ordinal sequential type attribute. I've also used the body mass index again, which is a quantitative and sequential attribute. There is no logical center to any of those. The average glucose level is also a sequential quantitative attribute. I have used gender and work type, which are both categorical. Um, while talking about data abstraction, one point that I missed is of derived attributes. A derived attribute is generally an attribute that we had to actually calculate to to make it representative in the graph. In our case, I have a derived attribute named the number of males and females, which is basically an aggregation of the number of males and females grouped by age and their work type. Since it's a numerical value, it is quantitative again, and it is sequential. Its orientation is sequential. I came up with the following example insights, which I wanted to work on, or which I wanted to validate and look into further. First one, self-employed workers have a higher chance of brain stroke as their jobs include not just getting the work done but also taking care of other aspects required to run a company. So I was guessing that self-employed workers should have a higher chance as their work is more stressful. Females, another example inside or hypothesis that I wanted to validate was whether females are more susceptible to having a brain stroke, as it's a general conception that females tend to overthink. Another one was that people with higher blood glucose levels should have higher body mass index, as extra glucose in the blood is directly converted to fat, which can again result to higher stroke rate or risk of stroke. Uh, in terms of task abstraction, there were two tasks that would have been helpful for particular for validating or analyzing the insights, the hypothesis that I had come up with. First one would be to identify which profession and which gender is at a higher risk. This would help me clarify if the self employed people and females are actually at a higher risk of brain stroke. The second would be to compare the number of male and female working in different professions and their susceptibility to having a brain stroke. This would again validate if females are actually at a higher risk of brain stroke or not. The marks and channels that I've used in the visualization are as follows. First of all, the data is represented in a 2D format. I have used both points and lines. The points are basically to represent the distribution of male and female in different body mass index and at different ages. The lines are used again to basically compare the number of males and females in a particular category of age and particular body mass and index. The channels that I've used for these marks are as follows. The points are colored based on the gender and size, which are based. The points are colored based on gender and they are sized based on the average glucose level. Since points represent categorical attribute, they are encoded as separate. They are also aligned because they have a common scale to place all these points separately, but they are not really ordered because they do not have any low to high or high to low order. They are scattered in a random manner. The lines that represent the number of males and females are encoded in an express manner. The colors are used to identify the gender. Since it's a categorical attribute, I've used different colors to identify the different gender. The size is to identify the average glucose level in blood. The bigger the size of the point, the more the average glucose level. The length is used to compare the number of male and female. The longer the line or the longer the bar in the chart, the more the number. The x coordinate of the scatter plot represents the body mass index, whereas the y coordinate represents the age. The bar graph is vertically represented with y-axis representing the gender. The x-axis of the bar graph represents the total number of male and female in a particular selection. Now let us look at the visualization that I came up with. This particular visualization is interactive and it also has these values that can be selected to look for particular types of people. Let's say or first, since a hypothesis was checking if self-employed people or workers have a higher chance of brain stroke. Let us actually see how they are distributed. Well, these are the data points for privately employed people. and as you can see, they are all separate and aligned with a common scale. Let us see how many data points are there for self-employed people. Well, as we can see, they are lesser than privately employed people. Government job government employees. Um, well, we cannot really compare if self-employed people are more than government employed people, but we can definitely see that uh, privately employed employees are more than the self-employed or the government employees, government working employees. So our first hypothesis is actually kind of wrong. uh, Privately employed employers are at a higher risk since clearly they are more in number. One of our hypotheses was whether people with high glucose level, uh, that is, people having a higher body mass index, are at a higher risk. Let us check that out. Um, we can see with the size of the dots that there are a lot of smaller dots than larger ones, which basically says that the rate of heart stroke is not really related to the body mass index or the average glucose level, I think. Also, let us see, in case of normal glucose level, is the body mass index higher or lower? We can see that the distribution is from the range of 14 to a range of 50. In case of pre-diabetic people, the range is again from around 16 to a maximum of 48. In case of diabetic people, the range is again from 14 to 48, which shows that the level of glucose does not really correspond with the body mass index of the person, and it's not a clear identification for whether a person is at a higher risk, because again the range of the categories in all the three cases of glucose level is more or less the same. Another one of our hypotheses was to check if the female tend to be more susceptible to brain strokes. If we look at the number of males and females in the case of diabetic people, we can see diabetic and privately. Let's just stick to privately employed people because they are more in number than the other ones. We can also quickly go over and check for self-employed and government employed employees later. So in case of diabetic people who are privately employed, there are clearly more number of females than males. Let us also check individual age groups. We can see that an early age male are more than female. In case of pre-diabetic people, again there are more female. We can clearly see with this length than male. Are there Okay, again at an early age in case of pre-diabetic people also there are more male. With a normal glucose level, clearly there's a wide gap between the number of males and females, and there are clearly more females at an early age. Okay, in case of normal there are more female in every age group. In case of all, let's just look at all the range for glucose level. At an early age, there might be a little more male than female, but we can see overall, let's look at self-employed and government employed people. Yeah, it is pretty clear from this bar graph that there are more female than male who are susceptible to brain stroke in terms of um, all work types and all the levels of blood glucose level. So our second hypothesis is kind of right. that females are generally more susceptible to having a brain stroke. And this is how I came up with the visualization. I went over the data abstraction, the task abstraction, and the how abstraction, that is the marks and channels. And you can clearly see that a categorical attribute is represented using different colors, which is an effective and expressive mark for a categorical attribute. The size of the data points is again a good a channel for representing the quantity of the blood glucose level, which is a quantitative attribute. The different lengths of bar are used as marks and channels for representing the number of males and females. The different colors of bars represent the different categories, whereas the length represents the number, which is a quantitative attribute, which is again the best way to to effectively express the quantity and the category. So here was a quick example of one of the projects that I did for my data visualization class. Um, the main insight that I came up with was that females and privately employed individuals are at a higher risk of brain stroke. And with this, I will end my presentation. And thank you, slide, for ending this. Thank you.